Chemical Kinetics, Part 2, Differential Rate Laws, Reaction Order, and using the method of initial rates to determine the reaction order. And we're going to do that for a simple reaction here with the single reactant A forming products. Differential rate laws relate rate to concentration. Let's start simple with a single reactant forming products. We could say that the differential rate law for a reaction that looks like that would be that the rate or speed of the reaction is equal to the rate constant, symbolized by the lowercase k, multiplied by an amount of chemical A, and we're going to keep track of chemical A using molar concentration, raised to the m power, where m is known as the reaction order. Now it's important to note that the rate constant k is different for every reaction, and it is temperature dependent. Typically, the higher the temperature, the bigger the value of k, and that means the bigger the value of rate. So if you're running faster, you have a higher rate of speed, right? So that means a faster reaction at a higher temperature, a higher value of k. So let's take a look at differential rate laws and orders of reaction for, again, single reactant reactions, where A is the reactant. We could say that the rate law, the differential rate law, is that the rate is equal to K times the concentration of A to the m power. The rate constant K times the concentration of chemical A raised to the order m. If we have a zero order reaction, m is equal to 0, then this expression just becomes that rate is equal to K, because any value to the 0 power is equal to 1. So notice here that the rate is constant no matter what the concentration. You can double, triple, change the concentration however you want. The rate's always going to be equal to the value K. In a first order reaction, that means the m value is 1. The differential rate law looks like this. The rate is equal to the rate constant K times the concentration of A. Remember that anything raised to the first power is just equal to itself, so we typically don't write that one exponent in there. And notice that here the rate is proportional to the concentration. So as this reaction is progressing, chemical A is going to be getting used up, right? It's a reactant. So let's say the reaction progresses to the point where the value of A is a factor of 1/2 of what it originally was. So A, concentration of A changes by a factor of 1/2. The rate would change by a factor of 1/2. If the reaction progresses so that the concentration of A is a factor of 1/4 its original value, then the rate would be 1/4 the original value. So the reaction would be slowing down there. Now, a second order reaction is one where the m value is equal to 2. So here we can say that the rate of the reaction, or the speed of the reaction, is proportional to the concentration of chemical A squared. This is the rate law. So what does that mean? If we let the reaction progress so that we have 1/2 of the original concentration of A, so it's diminishing by a factor of 1/2, 1/2 squared is 1/4, the rate would be 1/4 its original value. If we have 1/8 the original concentration of chemical A, 1/8 squared is 1/64, the rate would be 1/64 its original value. Now take note that the reaction order, the exponent value there, m, can be negative and it can be fractions. We're not going to be dealing with any of those here. And also, the reaction order for any one reactant, like chemical A there, is rarely greater than 2. So we just need to consider 0 and first and second order for reactions. So what does reaction order really mean? Well, let's take a look at that with some sample data. Let's say we have a zero order reaction where chemical A is forming products. The differential rate law would be that the rate is just equal to K. And that means that the rate's constant because K is a constant value. So rate is equal to K at any value for concentration. No matter what we change the concentration to, 1 molar, 0.5 molar, 0.25 molar, whatever, the rate of reaction would always be equal to K. Let's take a look at a first order reaction. So with a first order reaction, we can say that the rate of the reaction is equal to K times the concentration of A. So the rate's directly proportional to the concentration of A. Let's look at these data points here. We have 2 molarity, and the rate is 0.05 molar per second. We double to 4 molarity, and notice that the rate doubles and becomes 0.1 molar per second. We double the concentration again from 4 to 8 molarity, and the rate doubles again. It goes from 0.1 times 2, that's 0.2 molar per second. So when we increase the concentration by a factor of 2, the rate changes by a factor of 2. In a first order reaction, the rate is always proportional directly to the concentration. Here's a second order reaction, again for a single reactant A forming products. Here's what the rate law would look like. And that tells us that the rate is proportional to the concentration squared. So let's take a look at some data. Let's say that we have a concentration of 1 molar for A, and the rate is 0.01 molar per second. Let's triple that concentration and make it 3 molar, right? 1 times 3 is 3 molar. Notice what happens to the rate. It goes from 0.01 to 0.01 to 0.09. That's a factor of 9 times bigger. Well, 3 is not directly proportional to 9, but it is directly proportional to 3 squared, right? It's this number is proportional to the square of this number. That's what that square is telling us there. Change the concentration by a certain factor. You have to square that factor, and that's how it will affect the rate. So let's take a look at our next 2 data points. We go from 3 molar to 6 molar. Well, that's a factor of 2 increase. So the rate would increase from 0.09 to 0.36. Well, that's a factor of 4 increase, or 2 squared. So if you don't see that these values are constant, and you don't see that the multiplier here is exactly the same as the multiplier there, look for squared values, because then that would indicate a second order reaction. So let's go over determining reaction order. And what's really important here is that the order of reaction can only be determined by experiment. We have to have some experimental data that we can consider. We're going to be using the method of initial rates. The initial rate, the rate of the reaction at a short time interval at the beginning of the reaction, really the instant when the reaction starts, is measured at several concentrations of reactants. Let's take a look at some samples. Let's say we have A turning into products, again a simple type of a reaction here, and we run 3 different experiments. Now we get to set up some variables in the experiments, and what we're going to do is change the concentration. Notice that when we change the concentration and run the reaction, the rate of the reaction, and this is the initial concentration and the initial rate, the rate of the reaction right when the reaction starts, the rate of reaction stays constant. So no matter what I do to the concentration, the rate stayed the same. Well, that would indicate that there's a zero order relationship here, so that this rate law is equal to K times the concentration of A to the 0 power. It's just equal to K. So the rate constant is not affected by the change in concentration of A. And by the way, we would say that the rate's just equal to K, and it's got to be equal to 0.3 molar per second. That's the value of K. K is 0.3 molar per second, just as the rate is. That's a zero order reaction. Let's look at an example with a first order reaction. Now you wouldn't know the reaction order before you started. We're going to figure that out. Again, we have a single reactant A forming products. What is the rate law, and what's both the magnitude and the units for the rate constant? Here we have some experiments that we set up again, experiment 1, experiment 2, experiment 3, and we very deliberately change the concentration here by nice multiples, easy multiples. So we went from 0.12 molarity to 0.24, that's a factor of 2 increase, and then from 0.24 to 0.72, that's a factor of 3 increase. we run the reactions in all three experiments and measure the initial rate, the rate at the very start, for each reaction. In the first experiment, we get 0.003 molarity per second for our rate. In the second reaction, it's 0.006, and the third reaction is 0.018. So notice that when we double the concentration, the rate doubled. When we triple the concentration, the rate tripled. That's a one-to-one relationship between the change in the concentration and the change in the rate. So we can say that the rate law would be expressed as K times the concentration of A to the first power, or just K times the concentration of A. That's a first order rate law with respect to A. Remember that rate is directly proportional to the concentration of A in a first order situation. So what's the value of K? What we have to do there is take that rate expression for that first order in A and solve it for K, rearrange it so we have K by itself. Plug in rate and concentration, and we can use any experimental data here for rate and concentration. I'm just going to pick the smallest data points here, 0.003 for the rate and 0.12 for the concentration. Now the rate's in molar per second, the concentration is in molar, right? That's moles per liter per second and moles per liter. When you divide 0.003 by 0.12, it turns out to be 0.025. The molar cancels out there and we just get inverse seconds, or seconds to the -1 power, as the units. Now again, any experimental data, any line from this above table here, could be used to solve for the K value. And they might not be exactly perfectly the same, but they'll be awful close to being the same. Let's take a look at one more example. Let's say that we're going to determine the order of a reaction, and this time we're going to end up with a second order reaction. Now we wouldn't know that to start with, but that's how it's going to turn out here. So we have a single reactant A forming products. We've run 3 experiments, and again, we very deliberately decide what the concentrations would be, or whoever sets up the experiment would decide that. And you typically would want to use very simple multipliers. So we have a concentration of 0.5, we double it so that we have a concentration of 1, and then we triple it so we have a concentration of 3. Let's take a look at what happens to the initial rate when we run each of these experiments. In the first experiment, the initial rate is 2 molarity per second, then it becomes 8, then it becomes 72. So notice that we doubled the concentration here, the rate increased by a factor of 4. Well, that's not a 2 to 2 relationship. What is 2 to 4? Well, that's actually 2 to 2 squared. There's that square value. This is a second order reaction. We can see that again with the next 2 experiments, experiment 2 and 3. Here we triple the concentration from 1 to 3. And notice that the initial rate goes from 8 to 72. Well, that's a factor of 9 bigger, or 3 squared. So when you increase the concentration by a factor and the rate changes by that factor squared, that's a second order reaction. And we can say that the rate is proportional to the concentration squared. All right, so let's find the K value. We're going to take this rate law with the second order reaction there, solve it for K, and that turns out to be rate divided by concentration squared. We could choose any experimental data. Let's pick the smallest numbers from the first experiment. So we have 2 for the rate and 0.5 for the concentration. And remember, we have to square the concentration there. So what's 2 divided by 0.5 squared? It turns out to be 8. And what do you get when you take molarity, or molar per second, divided by molar squared? Well, one of the molars cancels out, and you get 1 over molar seconds, or molar to the -1 seconds to the -1. Remember, that's moles per liter to the -1 times seconds to the -1.